Okay, welcome everyone. Brian will be talking about exceptional super Lie algebras in M theory. Feel free to start whenever you're ready, Brian.
Cool, thanks a lot for the invitation, Flora, and everyone. I'm excited to be here. Yeah, so I'm going to talk about some exciting, what I think is exciting new work related to finding some sort of surprising appearances of exceptional Lie algebras in this mysterious thing that physicists call M theory. So I'm not a physicist myself, but I will try to give sort of a rough overview and taste of what M theory is. From there, I'm going to introduce, and by the way, my perspective on describing M theory, really its twist, are going to be describing some natural sort of moduli problems that even mathematicians can understand. From there, I'm going to move on to explaining where these exceptional Lie algebras pop up in this context. And after that, I'm going to mention a really powerful perspective called holography, which is obviously has its origin in physics, but actually provides some really interesting perspectives on once you come to accept that these exceptional Lie algebras pop up, it gives a really interesting perspective on them and also their theory of modules and other representation theoretic questions about these algebras. So sort of selfishly, I'll give you a little bit of a taste for what I like to do. I like to argue, or at least recently, why a handful of these exceptional super Lie algebras arise naturally in physics. I think on one hand, it's always good to explain, in my opinion, the sort of meaning behind why a certain algebra appears. And I believe that string theory, M theory is a very compelling reason for why these things arise. And then I'd like to use, more selfishly as a mathematician, to use inspiration from physics to gain insight into the representation theory of these algebras. And sort of at the practical level, this involves some sort of higher mathematics, which is not around in the usual theory of algebra or in the theory of vertex algebras. I really use derived algebra in a fundamental way. That'll sort of show its face a little bit in today's talk. I won't say too much about it, but I will mention it. And as far as other higher algebraic objects that are around, there's, for instance, what's really interesting to me are higher dimensional versions of vertex algebras. So I'll mention ordinary vertex algebras will pop up, and then I'll try to explain a little bit as to where higher dimensional ones are coming from, sort of in a natural way, from the physics point of view. Sort of generalizing the appearance of vertex algebras in chiral conformal field theory. Okay. So yeah, I wanted to start by giving a very selfish and biased recap of what I think M theory is. So physicists tend to understand this in terms of sequence of dualities, ultimately sort of dropping down to the world of string theory, which is sort of much better understood topic. But mathematically, even string theory is still really tough to comprehend. But there is a sector of string theory, or a type of string theory, called topological string theory. This is the sort of parallel between quantum field theory and topological quantum field theory, which we can understand in various contexts, sort of using various mathematical procedures. So, for instance, there's basically two sorts of topological string theories, the A and B model. Some of these may sound familiar to you. So in the A model, we have a slew of mathematical sort of interpretations of this topological string theory using things like the Fukaya category, theory of branes, etc. Gives us insight to what that topological string theory is. And leads to a lot of very powerful and beautiful mathematics, obviously. And on the B side, you're thinking more about complex manifolds, coherent sheaves on them. There's a beautiful appearance of cyclic cohomology related to non-commutative geometry, etc. So these are all things that are very sort of standard in mathematics, but lead to very nice interpretations of these topological strings. So back to, these are all about topological string theories. These are a bit too simple for what I'm going to talk about today. Very rich topic, obviously, but I really want to think about stuff related to actual string theory, superstring theory, or really up and above to M theory eventually. And luckily, my advisor, Kevin Costello and C. Lee, have proposed a simplification of full-on string theories or superstring theories, actually by using sort of enhanced and tweaked versions of these topological string theories, which we do understand quite well. And this is not sort of viewed as a full description of these string theories, but it's really just capturing some part of them. And this procedure is accomplished through a process called twisting. So if you know anything about twisting in, there's a more familiar thing about twisting supersymmetric gauge theories. And sort of for a nice class of supersymmetric gauge theories, you can produce via twisting topological QFT. So the most famous one here is, one of the most famous one here is Donaldson's theory, and related to a certain supersymmetric four-dimensional gauge theory, and interpretations of Donaldson invariance in terms of correlation functions in this topological field theory. But this twisting procedure also makes sense in the context of strings as well. And after doing so, what results is much simpler theories, which can be described in terms of these sort of well-combed methods of topological string theory. So you should think about sort of mixtures or tweaked versions of A and B models, as I mentioned above, which we can really say in terms on the A side, really that's about symplectic geometry, as I said. And on the B side, this is really about complex or holomorphic geometry. And you'll see in a moment when I characterize some twists of these strings or M theories, really what's going on is I'm describing some sort of very natural moduli space from the point of view of either symplectic or complex geometry. So great. So as maybe just let me reiterate, after twisting, these string theories, or at least in some limit, can be understood in terms of some really elegant moduli spaces. And from this point of view, after we get our hands on these moduli problems, we're free to ask questions about quantizations of them, in the same way that we ask about quantizations of the moduli space of Riemann surfaces in ordinary CFT and sort of objects related to that. From these descriptions of moduli problems, we can ask about more general versions of quantizations. And there's a rigorous mathematical way of doing this that I like to employ, which sort of uses techniques in homological algebra called the BV formalism. But I won't go that far into the hood in today's talk about that sort of thing. But once you have these descriptions, I'd like to emphasize that quantization is like a totally natural question to ask. An answerable question, more importantly. So let me do just an example to get a flavor of this sort of thing. So superstring theory is about strings propagating on a 10-dimensional spacetime. After doing these twisting procedures, what pops up sort of naturally is a complex structure on 10-dimensional spacetime. And the twists of these various string theories correspond to moduli spaces, which have as an input these complex 5-dimensional manifolds. Really, they're going to be Calabi-Yau manifolds. So a nice characterization of what's called the type 1 string. This exists on a Calabi-Yau 5-fold. This has a twist. It's called the holomorphic twist because it depends sort of holomorphically on all of the objects around. It's going to be stated in terms of complex geometry. And the moduli space of this string theory, or really the moduli space of solutions, you can think about this as, is given in the following way, as the sort of following schematic form. So the sort of thing I want to emphasize the most is this moduli space of complex structures first and foremost. So what the string theory is probing is it's probing this moduli space of complex structure on a fixed Calabi-Yau 5-fold. It's a very well-defined problem that we can ask about. And it's a little bigger than that. So what it is you look at this moduli space, you take its cotangent bundle, and you place the cotangent fibers in odd degrees. This is a totally classical statement I want to emphasize. Nothing quantum is going on here. But you can sort of see from this description that there's a residual symplectic structure around really a shifted symplectic structure. And that's the sort of starting point from the point of view of quantization. You can ask about how this symplectic structure quantizes in a rigorous way. So that's one of the features. The other key feature, as I said before, is that this complex geometry pops up in a very natural way. Okay. And a lot of these string theories in 10 dimensions are sort of variants of this sort of thing. They all have to do more or less with, after you twist at least, with complex structures or varying those complex structures, studying moduli spaces of complex structures. And you could also have other sort of data around. These are all, this type 1 string is what's called a closed string theory. There's also things called an open string theory, which have to do with studying principal bundles. So the moduli space for an open string theory, after you do these twists, generally looks like the studying holomorphic bundles, G bundles, principal G bundles. So one thing I mentioned a little bit about quantization. In a totally rigorous way, you can ask about quantization of this thing, and it turns out there's an anomaly. It doesn't have a quantization. That's actually a feature in this setting. Like, not string theories are very complicated. You can't always quantize them, but there is a mechanism which you can quantize. You can get rid of this anomaly. You can get rid of this obstruction, and that has to do with putting in some gauge theory, like I mentioned. The sort of open string side are described by these gauge theories, holomorphic principal bundles. And you can do so if you introduce a gauge theory for a certain group, SO32, for instance. That's one way to do it. This is a very famous mechanism called the Green-Schwarz mechanism in physics, but Costello and Lee gave a really pretty sort of interpretation of this just in terms of quantizing these nice holomorphic moduli problems. Sorry, this is Costello and Lee gave a sort of interpretation of this. Okay, so I won't say much more about strings. I'm going to move on to this M theory thing. So M theory, at least the best approximation that people tend to talk about, is a certain limit in which this theory can be described by a theory of gravity. And this gravity exists in 11 space-time dimensions. So M theory is really about an 11-dimensional theory. Even this supergravity theory is quite complicated. I challenge anyone to try to read a paper about 11-dimensional supergravity. I certainly don't. But after twisting, we can obtain a more explicit description, which is really nice, and that's really my starting point. I mean, we've characterized in a sense the twist of these guys. This is work with Surya Raghavendran, Ingmar Severi. We've characterized the twist of 11-dimensional supergravity. So there's actually two of them here. There's one that exists in a geometry that looks like a Calabi-Yau fivefold like we had before, cross R. So that's an 11-dimensional manifold, 11-dimensional smooth manifold. The moduli space depends on like the string theory I sort of mentioned just before, it depends on the complex structure on X. And this moduli space is equivalent to something that's, again, schematically of the following form. You look at the moduli space of complex structures on X, and you take its cotangent bundle again. But there's a very important procedure here that you have to do. A very important step is you don't just take the cotangent bundle, you take some twist of the cotangent bundle. So it's similar to twists of ordinary cotangent bundles, which you can do by a closed two form. So it's sort of close to that. I won't say much more about that. I'm going to point more algebraically in a minute to where what this twist looks like. It's extremely important on the algebraic side as well. There's another twist, which I'll just say a few words about, which exists on a geometry that's more natural to take a Calabi-Yau twofold or a hyperkähler manifold. cross R7. Even better, you could do something, people like to study this on a hyperkähler thing, cross a G2 manifold. But let me just say it on R7. Because the moduli space is a little simpler, it's equivalent to the moduli of complex structures just on Y. So all over the place, just moduli of complex structures are popping out. That may lead you to believe that these are just extremely simple theories, sort of tautological looking, but in a second, hopefully you'll see that they're very, very special, even if you don't believe in physics. Cool. So that ends my biased view of what is M theory. I think my answer here is to look at this moduli space. This is at least after twisting. So it's an answer most physicists may not be very happy with, but it is a piece of M theory that I can get my hands on. And now I can start to go to work with studying this theory. I can ask about things like its symmetries. That's where these exceptional algebras are going to come from. I can also ask about things which I'll do in a second about the way for vertex algebras model the observables of a chiral CFT, the operators of a chiral CFT. These are like vertex operators. You can ask about the observables of these higher dimensional theories as well. They have a very rich sort of operator product structure, just like in vertex algebras, which I'll say a little bit about. Oh, sorry. So I'm going to say some words about a few super Lie algebras, which are all called exceptional by Katz. So two things that will pop up. Superconformal algebras will pop up. So if you haven't seen a superconformal algebra, it's a super generalization of a conformal algebra. So you can look at conformal symmetries on any Riemannian manifold. So you can in particular look at them on affine space. I just look at Euclidean space. I don't do any Lorentz thing here. So you can look at conformal algebras on Euclidean space, and you can ask about sort of super generalizations of them. And there's a nice class of these super generalizations, which physicists call superconformal algebras. They contain in particular the supersymmetry algebra, which are very, very important for supersymmetric gauge theories and like Yang-Mills and things like that. Nahm and also Victor Katz classified all such superconformal algebras. There's a very important property here with the classification, which is you require these algebras to be simple. This, from the point of view of physics, is not clear to me at all why you would ask for such a thing, but it is a sort of a natural thing you can ask for mathematically, of course. And they classified all such superconformal algebras, which are simple in particular. And just like in the sort of ordinary conformal case, this is a theorem of Liouville. Once you go above dimension 2, I want to point out that these algebras all sort of collapse to be finite dimensional. So it's a very special property about conformal algebras in complex dimension 1, real dimension 2, that the conformal algebra is infinite dimensional. And the same exact thing happens for these superconformal algebras. So you only have these nice infinite dimensional superconformal algebras, which give rise to things like the super-Virasoro algebra in complex dimension 1. It just doesn't happen after you go past that. And it goes back to a theorem of Liouville, like I said. So that's one really nice classification scheme. Katz also, of course, did a lot of work. He also classified all simple infinite dimensional super Lie algebras. Many of these come in families. So many of these come in families. You could look at, for instance, the super Lie algebra of vector fields, say, vector fields on a supermanifold. Supermanifold like, say, C, I don't know, n/m. So this means that you have n bosonic coordinates and m fermionic coordinates. So a lot of these super algebras sort of exist in families. I could take that for any n and m. That's like clear. I have like a nice family there. But it turns out there's a handful of exceptions to this, just like in the classification of simple Lie algebras, ordinary simple Lie algebras. And somehow they pop up in M theory, in string theory, which is a new appearance of exceptional Lie algebras. There's another appearance of exceptional Lie algebras in M theory that aren't super. It's, as far as I can tell, not directly related to this. So it's really a new appearance of these exceptional super Lie algebras. And I'm going to talk about a few of them in a second. Right. So as I said, as a consequence of our characterization of supergravity or its twist, one of these exceptional superalgebras pops out really naturally. And it's in the following way. So this is really a corollary of that characterization that I just stated above about the twist of supergravity. And at this point in the talk, you can just forget about supergravity entirely and just think about algebras. So the universal symmetry algebra of supergravity on the following 11-dimensional manifold, which is as simple as it can be, C5 cross R. So I give C5 here. You remember I had to choose a Calabi-Yau structure. So I can give C5 just as flat Calabi-Yau structure. And I'm going to do that. I'll explain in a second what I mean by universal symmetry algebra. But the claim is that, or the result is that it's exactly this exceptional Lie algebra that Katz calls E5/10. This is one of these exceptional Lie algebras. Like I said, there's only a handful of these. Let me just say for a sec what I mean by universal. So if G is any other infinitesimal symmetry, so if G is any other Lie algebra or super Lie algebra, which is a symmetry of supergravity, if you like to think in terms of action functionals, it's the symmetry of the action functional of 11-dimensional supergravity. If you like to think in terms of moduli spaces, say they're cut out by some equations of motion, G preserves those equations of motion. Then there's a unique map from G into E5/10. I'm being a little sloppy here. What actually happens is that there's a central extension of E5/10, which is universal. I should have stated that more carefully, but I'll write it. You can sort of, for most of the talk, just remember E5/10. But it's a central extension.
Brian, I have a question. Sorry, can you remind us what this 5 and 10 are? Is it bosonic and fermionic? Because I don't remember the notation in that classification for E.
Yeah, so I'm gonna define E5/10.
Thanks. Okay, awesome.
Yeah, so I'll say where the 5 and 10 comes from. It wouldn't be my choice of labeling. I'm just following what Katz did. Yeah. They do have a meaning though. It's not completely even in this setting. They have complete. Yeah. Okay. So let me tell you what E5/10 is. So it's a super Lie algebra. There's an even part and an odd part. The even part looks at vector fields on C5. I mean, you can sort of take the proper thing to do from the point of view of simplicity is to take formal vector fields on C5, but you can sort of imagine them as being like holomorphic or algebraic. None of those issues will sort of play a role. And it looks at a subalgebra of those which are divergence free. So if you look at the standard holomorphic volume form on C5, which is just this object, so DZ1 up through DZ5, then you can ask that a vector field preserve this thing in the sense that its Lie derivative along into 0. So that's a subalgebra of vector fields in C5. That's the even part. That's all the even elements. And that's a Lie algebra in the natural way. The odd part looks again at a subspace of a very familiar object. What you do is you look at two forms on C5. Again, you can do holomorphic or algebraic, formal, whatever. And you can ask that the two form be closed. So I just mean closed for the de Rham operator, d alpha is 0. And this is another, so this thing is obviously a module for vector fields, for divergence free vector fields just by the Cartan formula. But there's a single interesting bracket. So the even part clearly acts on the odd part. There's a single interesting bracket which takes two odd elements and spits out an even element. And without this thing, this algebra would not be simple anymore. It's very important that you have this extra bracket. And it looks like the following thing. So you can take two closed two forms, alpha and alpha prime, and you can just wedge them together to get a closed four form. But if I use since I'm on a Calabi-Yau fivefold, closed four forms are the same as four forms. I can just contract with a vector field to identify this with, I can contract the holomorphic volume form with a vector field, of course, to get a closed four form, or to get a four form. And I can ask what happens to if this isomorphism, under this isomorphism, if I started with a closed four form. And the answer is you exactly get a divergence-free vector field, thankfully. So the Calabi-Yau form identifies as a vector space closed four forms on C5 with divergence-free vector fields on C5. So therefore, this thing actually lands me back in the even part of the Lie algebra. So it is well defined. Checking the Jacobi relations is a fun exercise. Great. I did want to make one remark. So schematically, I wrote this moduli space of M theory as T star of the moduli of Calabi-Yau fives. And I was just looking at the Calabi-Yau five, which is C5 cross R. Sorry, C5 here, just the flat Calabi-Yau fivefold. And it's clear the interpretation of the even part, it's just acting by automorphisms of deformations of complex structures on C5. Given any other, the algebra of divergence-free vector fields is exactly the automorphisms or the infinitesimal automorphisms of deformations of complex structures, which preserve the Calabi-Yau form. That's how you should think about vec theorem. The closed two form part comes from the fact that I'm taking the cotangent space to this moduli space. So those are the symmetries sort of that are acting on that act on the fibers of this. But I told you something very important was that there's this weird twist going on here. And this twist is exactly responsible for this bracket that we have between two odd forms. So without that twist, you wouldn't see this, and without this, it wouldn't be simple. So somehow everything comes together in a crazy way to give you this simple Lie algebra, exactly from the twist of 11-dimensional supergravity, which is the very surprising, one of the very surprising things about this story. Cool.
And without the twist, you would just get the Lie algebra and a module for the Lie algebra.
Yeah, exactly. It would just
Gotcha.
you would just turn. So you're free to turn this thing off. You can totally turn this bracket off, and that's a fine Lie algebra. Because, like we said, the even part is just an ordinary Lie algebra. The odd part is a module for that thing. You can take a square zero extension and get a new super Lie algebra. Thinking about this module just as sitting in odd degree. That's like a totally fine way to build a super Lie algebra. But you're deforming this in a very particular way in order for it to be simple. And it's exactly the same deformation of this cotangent bundle, it turns out. Yeah. I don't have a great explanation for this. It just sort of happens. I mean, I have a great explanation for how this bracket arises, but I don't have a great explanation as to why exactly this sort of very geometric thing on the sort of field theory side corresponds to deforming you to a simple algebra. I don't have any intuition for that, but I will roll with it. So the next thing I want to talk about in M theory, what people like to think about are what are called extended objects, and these are known as branes in physics. So this is important, but a very mysterious brane in M theory is called the so-called M5 brane. And you think about these branes as supported not everywhere on the 11-dimensional spacetime, but they're supported on some submanifold. So M5's, the counting is a little weird. It corresponds to a 6-dimensional object. Physicists don't like to count time as a direction into these labelings. So it's really in Euclidean space. It looks like R6 sitting inside of 11-dimensional spacetime. But it's very hard, even in the physics sort of level of rigor, to describe this object explicitly. And any description you find leaves a lot to be desired. Nevertheless, this theory, at least the way mathematicians and physicists can get their hands on it, has led to a lot of beautiful mathematics. Some of these twists are in the math world are sometimes called theory X, though that terminology is somewhat polarizing. But if you've seen the terminology theory X before, it's related to this thing. So one very beautiful piece of mathematical physics is the AGT correspondence. This gives a relationship between this theory I mentioned before related to Donaldson theory, 40n equals 2 super Yang-Mills, the partition function of such a thing, and the conformal blocks of a certain chiral CFT, a 2-dimensional chiral CFT. This 6-dimensional theory, this thing on R6, gives a sort of unifying perspective on this correspondence. Another unifying perspective that it gives is insight into the Langlands program. And this passes through sort of what's called the dimension reduction of this theory down to 4 dimensions, which gives maximally supersymmetric 4-dimensional Yang-Mills theory, which people have studied as giving a very beautiful sort of context for the Langlands program, Langlands correspondence. I'm not going to talk about either of those in too many, maybe the first thing might pop up again in a sec, but I want to say one thing that we do know about this 6-dimensional theory, whatever it is that it's super conformal. That is, the classification scheme that I mentioned before by Cass and Nam, we know what the 6D superconformal algebra is. There actually is a unique one in 6D, meaning, what do I mean by that? I mean that there's a unique thing which extends the conformal algebra in 6D on R6. After complexifying, I'll say what it is in a second, what it is after complexifying at least, or in the Euclidean signature. And we know that whatever the 6D theory is, it has to be a module. It has to be acted upon by this superconformal algebra. That's what we do know. This superconformal algebra I want to emphasize before twisting is a finite dimensional thing. Of course, I mentioned this earlier, but I want to emphasize that again. So my collaborator Ingmar Siberi and myself have also characterized the twist of this M5 brane theory, this thing on R6. Again, it depends very nicely on complex structures. It doesn't behave in sort of the same way as these theories of like M theory or string theory. It doesn't involve deformation of complex structures. It feels quite a bit more different, but it's still given in terms of a nice moduli problem. And we know how to characterize at least the simplest version of this thing, which people call the abelian 6-dimensional theory. It's really the simplest one that people can get their hands on. And it's equivalent to the following moduli space. So here X is a Calabi-Yau threefold now. So I'm thinking about, before twisting, it was something on a 6-manifold. Like above, I was just sort of saying it was R6. After you twist, it turns out to exist on any Calabi-Yau threefold, really actually any threefold if you choose some more data. But it's easiest to say when X is Calabi-Yau. And it's of the following form. So you look at the moduli problem, which is, you look at the space, which is the intermediate Jacobian variety of X. More honestly, we're doing sort of a derived, sort of infinitesimal version of this variety. But I'd like to think about it just as being related to this intermediate Jacobian thing. And there's two pieces. There's one piece that looks like that, and there's one piece that looks very simple. It just looks like a space of holomorphic maps. So it's like a mapping space from X to a complex two-dimensional space, vector space even. So it has these two pieces. This is sort of, I'm making an attempt here to make a global description, but there's an infinitesimal description of this space. That is, if you look at the tangent space of this whole thing at a particular point, so at a solution, that is, my favorite holomorphic map is the constant holomorphic map. And you can look at the sort of a preferred point in the intermediate Jacobian variety as well. And this tangent space has an explicit model in terms of a cochain complex. So I'm looking at the derived tangent space, or the tangent complex. And it looks like this, which again involves very natural objects on the Calabi F3. So it's a cochain map, it's a cochain complex, so it's spread out in a few degrees. Degree -1, it's 2 forms, holomorphic 2 forms, degree 0, it's 3 forms. You can sort of see that this is related to the intermediate Jacobian variety. This thing's related to this mapping space. And there's a simplification of this. We could just more or less apply the cohomology with respect to that operator I wrote down. Or you could just think in terms of resolutions. This complex, at least on the top line, is exactly the complex which resolves the sheaf of closed 2 forms. So in degree -1, you have the space of closed 2 forms on this Calabi F3, and in degree 0, you have holomorphic functions with values in C2. I mean, this mapping space is sort of boring. I took the tangent space, but it was already affine because its target was affine. So this thing is exactly the mapping space on this side. That's the thing in degree 0. So this is, I would like to view as the most concrete way to get one's hands on the simplest M5 brane theory, this abelian theory. It's something whose solutions to equations of motion involve a closed 2 form, which you think about as having odd parity, and a holomorphic function valued in C2. So I told you I would say what the 60 superconformal algebra is, at least in the Euclidean signature after complexifying. You can think about it as OSP 8/2. This is an explicit supermatrix Lie algebra. After you twist, in the same way that I was saying before, which is you can understand as taking the cohomology with respect to a preferred element in here called Q. It's called the supercharge. So Q lives in here. You can look at the adjoint action of Q as long as Q squared is 0. This again is a cochain complex. The twist is taking the cohomology with respect to this thing. In the language of algebras, I'm really just commuting a commutant. So this commutant is OSP 6/1. This is a nice, fun calculation to do. I haven't told you what Q is, but there's a Q whose commutant is OSP 6/1. And this is the thing I would really think about as being a symmetry of the twist that I just mentioned. So OSP 6/1, I won't tell you exactly what it is because I'm going to tell you something much more interesting in a second, but its even part is SO6 cross SL2. The terminology here is that SL2 I'm thinking about as the infinitesimal symmetries of symplectic space C2, which I like to call SP1, but you can think about it just as SL2, of course. So here's our result here. So there's an embedding of this finite dimensional algebra, OSP 8/2, just a matrix algebra. After you twist, still get another matrix Lie algebra. Embeds inside of another exceptional Lie algebra called E36, different than E510. I'll tell you what it is in a second, but this is another one of these exceptional algebras that Katz classified as not belonging to one of these families, one of these towers of simple Lie algebras. It's exceptional. Furthermore, so that's a cool thing, like fine. A lot of I'm sure a lot of finite dimensional algebras sit inside of E36, but the crucial thing is that E36 is a symmetry of the 6D theory that I just described. That is, this object here is a module for the super Lie algebra, which is E36. So just by following through the sort of physics picture, we know OSP 6/1 acted, this finite dimensional algebra. So the content here is extending this OSP 6/1 module structure to this infinite dimensional Lie algebra, which is E36. And that's not at all obvious before twisting. It's not at all obvious from the usual point of view of the M5 brane. So in this setting, one way I like to think about E36, and I'll say a few more words about this in a second after I tell you what it is. You should think about it as being the correct higher dimensional analog of at least the positive part of the Virasoro algebra. So I'm really thinking about this E36 as playing the role of the superconformal or conformal algebra in complex dimension 1. And once I tell you what it looks like, you can sort of get a feel for why that's maybe a reasonable thing to say. So E36 sort of has a similar description of E510. So its even part consists of holomorphic vector fields on C3, as well as SL2 valued functions on C3. So these are both infinite dimensional algebras, of course, vector fields and SL2 valued functions. They talk to each other. Vector fields, of course, act on functions. So the even part's a Lie algebra. It's a square zero extension. Sorry, it's not a square zero extension, but it's an extension of vector fields. SL2, of course, I'm just using the usual commutator. And the odd part is given by one forms on C3, but doubled. So you take 2 copies of one forms on C3. The odd part, again, is a module for both the summains and the even parts. So vector fields act by Lie derivative, and SL2 acts just by rotations on C2 in the fundamental way. And then you just multiply functions onto one forms. So there's natural module structure. All the richness, again, is in the bracket, which goes from odd to even. It has this following form here. So I don't need to say too much about it because it won't be that important. But there's an odd even bracket as well. One thing I would like to point out is that one can make sense of this algebra on more than just affine space. So you see how affine space sort of appeared very naturally in each of these dependencies. So we looked at vector fields on affine space, functions on affine space, one forms on affine space. We can do that. But it's totally fine to replace this by an arbitrary threefold. I can make sense of vector fields on a threefold, functions on a threefold, one forms on a threefold. On the threefold, which is C3/0, remove the point, so punctured C3, you get something that's very, very akin to the Witt algebra. It's like a higher dimensional analog of the Witt algebra. Now, people would say this is not a very interesting thing to do by a very famous theorem called Hartog's theorem, which says that functions on C3/0 is exactly the same as functions on C3. So from the point of view of doing something like the Virasoro or Heisenberg algebra, this is a very silly thing to do, is to look at punctures in higher dimensional spaces. This is part of the reason why higher dimensional Virasoro algebras have not really crept into math in the past. But there's a very key insight here, which unfortunately I haven't said much about, and I probably won't say too much more about, which is that you can make sense of this in a very nice way if you derive everything. So instead of looking at literal functions on C3/0, you should really be looking at derived sections at C3/0. And you think about this thing as a DG algebra. And this DG algebra contains a lot more information than functions because C3 minus the point is not affine anymore, unlike dimension 1. This is exactly what happens in dimension 1, which saves you. Punctured C is a Stein manifold, it's affine. So its functions, which are just Laurent polynomials or Laurent series, of course, is a very interesting thing to do from the point of view of like conformal field theory. It gives rise to the algebras like the Heisenberg, the Virasoro, like I said. If you play the same exact game in higher dimensions, you'll get nothing interesting, but you will if you derive things, which is a very, very sort of, it's a quite a new story. There's work in the direction of doing this for Kac-Moody type algebras, higher dimensional Kac-Moody algebras, started by Kapranov and collaborators. I've thought a bit about this from the point of view of holomorphic field theory in higher dimensions, sort of as a generalization of chiral conformal field theory. So there's a very rich story here about doing this derived procedure, which I won't say too much more about. But I would like to mention one problem, which is if you do this on C3 minus a point, what you end up getting is not a super Lie algebra anymore, but it's really a super DG Lie algebra. There's a differential around because we have this DG structure already when we look at derived sections. So really the higher dimensional Virasoro, it's more accurately a DG algebra. It's a super DG Lie algebra. And it's a very interesting problem to classify central extensions of this thing in the same way that we know how to classify extensions of the Virasoro algebra. Play a very important role in conformal field theory. Central charge is, of course, one of our favorite ways to characterize vertex operator algebras. So the central charge or central charges of this higher dimensional version will play, I think, an equally important role from the point of view of representation theory. Okay, any questions on this? So far we found these two sort of exceptional algebras coming from what I tried to argue is being related to this mysterious object in physics called M theory. So it's giving us some insight into what physicists mean by that. So next thing, this section is maybe starts out a little bit more hand wavy, but at the end actually really gets down to some cool perspectives on a class of representations for these algebras that I just mentioned. So in physics, there's this very rich story which goes under the term holography. And what this does is it relates these theories of gravity that I've been talking about, like M theory, on special sorts of spacetimes called anti-de Sitter spacetimes, which I won't say anything about because I don't think about Lorentzian or Riemannian manifolds, but this is where holography is usually formulated. And it describes such things in terms of, in a sense, some much simpler objects. Describes them in terms of the theories which live on the branes in those supergravity or string theories. At least in the case where you have a large number of branes. So you can think about branes here, as we talked about before, as living sort of inside of the supergravity theory. They live on like defects or like submanifolds. And you can ask about stacking a lot of these branes together, which from the point of view of gauge theory corresponds to looking at gauge theories with values in n by n matrices, for instance. So roughly these theories on the brane are given by moduli spaces which describe principal bundles for the group GLN roughly. And as n goes to infinity, the simplest version of holography, or sort of very simplified version of holography, states that there's basically some equivalence between these two pictures. If you can understand one, you can totally understand the other. Of course, in physics context, you have to let out of caveats. I have to say that. No, Kevin Costello, Lee, Gairo, Paquette, a lot of mathematicians and physicists have proposed a simpler but still very interesting version of this principle, this duality between supergravity and theories like gauge theory on branes, which involves something called causal duality, which is sort of, I mean, maybe slightly something more general than what you're thinking of causal duality, but reduces in the case of algebras to just ordinary causal duality for algebras. And roughly what it says is that the algebras, it sort of codifies the statement mathematically. It says that if you look at the algebra of observables on this universal brane, as you take a large number of branes to infinity, and you look at the algebra of observables in gravity, they're basically causal dual to one another. Now, making sense of the statement takes a long time, so it's like very sketchy at this level. But roughly, I would like to, I'm sort of just trying to emphasize that there's this at least proposal for a very systematic relationship or codification of this mysterious thing called holography. And on one side, you should understand what gravity is, and the other side, you should understand what these sort of theories on branes are. You can understand both sides in my language using what are called factorization algebras, which are sort of generalizations of things like vertex algebras, which make sense not just in complex dimension one, but in arbitrary complex dimension or in arbitrary dimensions. But more sort of precisely for this talk, I want to just emphasize that one of the main outcomes of this principle is the very interesting role of a class of infinite dimensional algebras which arise from the gravity side play. In the same way that we've already seen where these exceptional algebras have arisen from at least twists of some version of gravity. And maybe just to say a few words about a much more simplified version than even what I've been saying, but still extremely rich. So Kevin Costello studied a version of this M5 branes where you also do some sort of equivariant cohomology or some further sort of reduction. So instead of looking at a full 11-dimensional theory, what you do is you basically take the equivariant cohomology for 3 different circle actions which act in this way, sort of in this sort of, which looks like an ad hoc geometry. It turns out to be very natural to do such a thing. But what this localization or equivariant cohomology ends up doing for you is it basically collapses all of those copies of R2 down to just a point. So at the end of the day, you get a very simplified version of M theory or 11-dimensional supergravity, which just exists in 5 dimensions. And he told a very beautiful story, proved a very beautiful thing, which is that this 5D theory has an interpretation as a sort of non-commutative version of Chern-Simons theory. Which you can really get your hands on. So for instance, the observables take the following form. So here I'm talking about Lie algebra cohomology. So at least this is a classical statement. So what you do is you look at, so here there's a K around, which wasn't obvious at all, but for the Lie algebra GLK, K is just an integer. It has some, it plays a role in this gravity story, but we don't have to say so much about it. But I just want to point out what the observables look like. It's a very concrete looking object. You look at the Lie algebra cohomology of this current looking algebra. So here GLK is valued in 2 algebra polynomials with 2 variables. So there's an obvious bracket there, but there's a non-commutative deformation of this, which turns on the Poisson bracket between Z and W. That's what I meant by non-commutative above. So here I'm viewing C2, which are the coordinates of C2 are Z and W, and I'm viewing this sort of in the sense of deformation quantization. So I'm turning on some Poisson bracket, which enters into the symmetries of this theory. There's an even, so we could do the same thing now for branes. So they live along, before they lived along this 6-dimensional space, these M5 branes did. So the branes now, after you do this localization, live along a complex 1-dimensional space, or a real 2-dimensional space, so much easier. And what this principle of Koszul duality or holography tells you, or gives you as an ansatz for what this universal theory on the brane should be. And because it lives really naturally in complex dimension 1, it's no surprise that it's given by, its description is in terms of some vertex algebra. And a conjecture of Kevin, which is proved it in various versions, is that the vertex algebra on a large number of these M5 branes, which we don't really understand directly, but we do through this sort of perspective of Koszul duality, after this localization down to from 11D to 5D, and then from the 6-dimensional brane down to a 2-dimensional brane, is a very familiar looking object, but rich object called the W1 plus infinity algebra. So I mean, the W1 plus infinity is a limit of W algebras for the simple, semi-simple Lie algebra Ln as n goes to infinity. So these somehow more exciting algebras pop out of M theory in this way after doing this localization. Let me skip this because I'm sort of out of time. But now what I want to do is return to my settings. So before doing this localization where I got rid of all of those like R2 directions, I got rid of 6 directions by doing this localization. So I want to turn to my picture where really I'm thinking about the M5 branes as living on some complex threefold inside of the 11-dimensional space. And what we've seen is that basically this 11D supergravity after we twist is controlled in a sense by this Lie algebra, exceptional Lie algebra E510. And Katz writes down sort of an amazing decomposition of E510, which has, I'm going to argue, some beautiful interpretation, or I'll start to hopefully give you an interpretation in terms of holography. And he does the following thing. So he says that E510 can be decomposed in the following way. So this is like a grading, if you like, on E510, which is concentrated in degrees bigger than or equal to -1. And it has the following really nice property that the thing in degree 0 is exactly E36. And because it's a grading, you know the thing in weight 0 is itself also a super Lie algebra. And the super Lie structure is exactly the same one you have for E36. So it's, if you squint, you can sort of see some holography going on here. I told you the really, really rough picture of holography is that some supergravity theory that exists in some large number of dimensions should be very closely related to some theory on a brane which exists in a dimension smaller. It's where the brane is supported on. So you see this grading is sort of picking out a smaller dimension, symmetries in some smaller dimension, which is exactly E36 as we started to argue before. And another nice property is that, in using this fact in particular, every other U of J for J not equal to 0 is a module for E36 that is grading. So in particular, one module you can get your hands on is the lowest level module. So when J is -1, turns out it is, or rather its dual, is exactly that module I wrote down above, this thing that exists, this thing that describes the abelian M5 brane theory. So somehow Katz also knew that, or was also telling you something about M5 branes even in this setup, which is sort of amazing. He would not have said it like that, of course, but it just pops out like totally naturally from this grading. So in that broad sense, which unfortunately I don't have time to, I'm very excited about this. I don't have time to keep yelling this at you because I'm running out of time, but I really want to think about this as some holographic decomposition that I'm going to use to hopefully in the future prove some really cool things about the representation theory of E36 and interpret these higher dimensional modules as being related to sort of higher analogs of higher spin modules for the Virasoro algebra. And really, if I'm going to be like completely, maybe this is a little bit overstepping, but this decomposition is very, very parallel to this decomposition of the W algebra, as thinking about the W algebra as sort of filtered by operators of higher and higher spin. So there's some higher W algebra stuff going on here too, I think. But as for some concrete things, with Serial Argavendron, we've computed some E36 characters of these UJs, and we've confirmed expectations in physics, which is really cool. So it really tells us we're on the right track from the point of view of physics. And I think I just said this, but I'll say it again. These higher spin modules, these higher J's, you should really think about as I want to think about as being higher lifts of this filtration of this W1 plus infinity algebra that I mentioned above. And using this holographic setting, one thing you can do is you can find connections to much more complicated M5 brane theories, which are non-abelian, using this principle, which is even progress in the style of physics. Physicists don't I don't think at least have as concrete of a description of the non-abelian M5 brane as the one I'm describing here, at least after the one after you twist. Yeah, so maybe I'll just say a last few words, some really more concrete evidence of things that we've checked. So I've been going on and on about why I want to think about E36 and these higher dimensional modules as being lifts of things that you know very well in the world of CFT. And I can make this explicit through deformations of these algebras and modules. So deformations, I mean here, is turning on some adjoint style differentials. So here, it's like bracketing with some fixed thing Q, where Q is in E36, which is square zero. So it's like a Mara-Cartan element. You can ask to deform these things by an operator which is like this, which you interpret as taking you can interpret as taking the cohomology with respect to this sort of operator. So there's special sorts of deformations which do the following thing. So you can look at this E36. There's this central extension, which we sort of have not characterized completely, but we sort of abstractly know how it works. And if you evaluate it on this punctured C3, after this deformation, you exactly recover the Virasoro algebra. You can take this abelian M5 brane theory and do the same deformation. You exactly recover the Heisenberg algebra. So I mean the Heisenberg algebra as like a central extension of polynomials, Laurent polynomials in one variable. And according to this filtration that I mentioned before, you're very, very tempted to make the following expectation, which is that if you look at the sum of all these modules in this decomposition, at least after dualizing, there was this weird thing with Kojoule duality, which I was a little sloppy about. The expectation is that it returns Kevin Costello's story with W1 plus infinity algebras. And this is a statement about, this could be a statement either about vertex algebras or about associative algebras, whatever your favorite way to think about W algebras is. There's both versions. Yeah, so let me stop there because I'm already like 2 minutes over time. Yeah, so I'm done.
Thank you so much. Okay, let me stop the recording and we'll open up for questions.